The story of the largest stars does not begin with brilliance. It begins with hesitation. Objects that nearly become stars but never quite cross the line. To understand size in astronomy, it helps to start not with extremes, but with thresholds. Nature does not leap from planets to suns in a single step. It inches forward through compromise. Consider a gas giant like Jupiter. It is vast by planetary standards, composed mostly of hydrogen and helium, the same elemental ingredients found in stars. Yet composition alone is not destiny. What matters is pressure. Jupiter's interior, despite its bulk, never becomes dense or hot enough to force atomic nuclei together. It shines only by reflected sunlight and faint internal heat left over from its formation. Between planets and stars lies a murky category of objects that complicates any simple definition: brown dwarfs. These are bodies far heavier than Jupiter, dozens of times its mass, but still incapable of sustaining full hydrogen fusion. Some can briefly fuse deuterium or lithium, generating a weak internal glow, but this process is fleeting and incomplete. Adding more mass to a brown dwarf does not inflate it the way air fills a balloon. Instead, gravity compresses it further. The object grows denser, not larger, its electrons resisting collapse through quantum pressure rather than thermal expansion. These failed stars occupy an uncomfortable middle ground, luminous enough to confuse, but fundamentally unfinished. A true star is born only when gravity wins decisively. Once an object accumulates enough mass, roughly 100 times that of Jupiter, its core reaches temperatures of millions of degrees. Hydrogen nuclei begin to fuse into helium. Energy floods outward. The object stabilizes, balanced delicately between inward gravitational collapse and outward radiation pressure. This equilibrium marks the beginning of stellar life. Stars in this phase are known as main sequence stars, and they are far less uniform than they might appear. Mass governs almost everything about them: brightness, temperature, color, and lifespan. Small stars burn gently, sipping their fuel over timescales that dwarf the current age of the universe. Larger ones burn recklessly, consuming themselves in cosmic moments. The smallest true stars, red dwarfs, barely sustain fusion at all. They glow dimly, their surfaces cool by stellar standards, their energy output modest. Yet their restraint is their strength. By fusing hydrogen slowly and efficiently, red dwarfs can endure for trillions of years. They never swell into giants. They simply fade, quietly, long after more dramatic stars have come and gone. Stars like the Sun occupy a middle ground. Hotter, brighter, and far more massive than red dwarfs, they live faster lives. Their energy output reshapes surrounding space, governs planetary climates, and drives complex chemistry. But even these stars are temporary structures. Their fuel supply, though immense, is finite. At this stage, size still correlates weakly with mass. Doubling a star's mass does not double its radius. It multiplies its luminosity. Some stars, only modestly larger than the Sun, shine dozens or thousands of times more brightly, their surfaces blazing with energy. Already a paradox emerges. The most powerful stars are not necessarily the largest. That paradox deepens as stellar evolution continues. Because the truly colossal stars, the ones that challenge imagination, are not defined by how they are born, but by how they age. And to reach them, stars must first begin to unravel. In the stellar world, more is rarely better. As stars grow heavier, they do not simply scale up in size like architectural models. They become unstable, volatile systems where balance is constantly under threat. Mass, once the key to ignition, turns into a liability. Among main sequence stars, increases in mass produce disproportionate effects. A star twice the mass of the Sun does not burn twice as brightly. It can radiate tens of times more energy, its surface heated to temperatures that shift its color toward white or blue. The physics behind this is unforgiving. Higher mass means stronger gravity. Stronger gravity means higher core pressure. Higher pressure accelerates nuclear fusion. The result is a star that burns hotter, brighter, and much faster. These stars live abbreviated lives. While a star like the Sun enjoys billions of years of stable fusion, massive blue stars exhaust their hydrogen in mere millions. They are cosmic mayflies, intense, luminous, and short-lived. Entire populations of such stars can be born and die, while calmer stars barely notice the passage of time. Yet even among these giants, size remains restrained. The most massive main sequence stars known contain dozens of times the Sun's mass and emit millions of times its light, but their physical diameters are surprisingly modest. Gravity keeps their outer layers tightly bound. They shine not because they are large, but because they are furious. At the upper edge of this regime exist stars so extreme that they challenge our understanding of how stars form at all. Their radiation output is so intense that it actively resists further growth. As gas falls inward during formation, powerful stellar winds and radiation pressure push it back out. This creates a natural upper limit to stellar mass. Beyond a certain point, a star cannot easily grow by accretion. Some of the most massive stars known may have formed not in isolation, but through collisions and mergers inside dense stellar clusters. These extreme stars bleed matter continuously. Their surfaces are not calm, glowing spheres, but turbulent boundaries where atoms are torn away and flung into space. Every second, millions of tons of material escape, carried off by radiation-driven winds. Gravity holds on by a thread. Despite their violence, these stars are still relatively compact. Even the brightest and most massive among them may span only a few dozen times the Sun's radius. Their brilliance masks their restraint. They are engines, not balloons. The path to true enormity does not lie in continued growth along the main sequence. It lies in transformation. When hydrogen in the core runs low, fusion slows. Gravity regains the upper hand. The core contracts, heating rapidly, while the outer layers respond in a counterintuitive way. They expand. This marks the end of a star's stable adulthood and the beginning of its most dramatic metamorphosis. Fusion shifts to shells surrounding the core. Energy output increases, but it is redistributed. The star swells, cools at the surface, and enters a new phase of existence. This is where stars stop being dense points of light and become structures of almost incomprehensible scale. The largest stars in the universe are not defined by how violently they burn, but by how loosely they hold themselves together. When a star leaves the main sequence, it abandons restraint. The balance that once kept it compact dissolves, and gravity no longer dictates a simple geometry. The core tightens, compressing under its own weight, while the outer layers respond by drifting outward, as if released from an invisible tether. The star does not explode. It relaxes, catastrophically. This transformation produces red giants and, for more massive stars, supergiants. Their surfaces cool as they expand, shifting their light toward red and yellow hues, but their total energy output often increases dramatically. What was once a concentrated source of power becomes an immense, diffuse structure. A star only modestly heavier than the Sun can expand to tens or even hundreds of times its original radius, engulfing regions of space where planets once orbited. In stars similar to the Sun, this swollen phase is temporary and relatively orderly. But in high-mass stars, expansion becomes an act of excess. These stars evolve into hypergiants, objects so large and luminous that traditional stellar categories begin to break down. Their outer layers are tenuously bound, their atmospheres distended to the point where the concept of a surface becomes ambiguous. Blue hypergiants represent one extreme. Though still hot, they possess radii hundreds of times greater than the Sun's. Their radiation output is staggering, and their stellar winds are relentless. Material streams away continuously, forming vast envelopes of gas that blur the boundary between star and surrounding space. These objects are rare, not because the universe lacks mass, but because such configurations are fleeting. They are stars in transition, shedding weight as quickly as they burn fuel. Yellow hypergiants push this instability further. They occupy a narrow and precarious region of stellar evolution, where internal processes oscillate between contraction and expansion. Their brightness fluctuates. Their size can change on astronomical timescales that are short enough to be observed. Only a handful are known, suggesting that this phase lasts little more than a cosmic moment. Then come the red hypergiants, the most physically expansive stars ever identified. These are not stars in the conventional sense of tidy spheres of plasma. They are sprawling, irregular structures with diameters comparable to the scale of planetary systems. Their gravity at the surface is so weak that atoms drift away almost unopposed. Radiation, convection, and pulsation combine to strip mass continuously, turning the star into a slow-motion storm of escaping gas. Measuring such objects is extraordinarily difficult. Their brightness overwhelms detectors. Their distances are vast. Their shapes are unstable. Even small uncertainties in observation translate into enormous uncertainties in size. As instruments improve, estimates change. Records are broken, then quietly revised. Some red hypergiants may exceed 1,000 times the Sun's radius. A few candidates may stretch even farther, their outer layers extending so broadly that light itself takes hours to cross them. In these stars, density is so low that their outer atmospheres are closer to a laboratory vacuum than to anything resembling solid matter. These stars are not sustainable. They represent a terminal extravagance. As mass drains away, the core continues its work, forging heavier elements in successive stages of fusion. Iron accumulates, an endpoint that offers no energy in return. When the core can no longer support itself, the story ends abruptly. Gravity collapses the center. The outer layers rebound violently. The star detonates, dispersing its substance across interstellar space. But before that final act, there exists a brief window in which the universe permits excess, where a star can grow larger than any stable structure ought to be. The question is not how large such stars can become in principle, but how long the universe allows them to exist at all. There is a temptation to ask which star is the largest, as though the universe maintains a leaderboard. In practice, this question resists a clean answer. The largest stars are not fixed entities with sharply defined boundaries. They are evolving processes, caught briefly in states that cannot last. Red hypergiants sit at the edge of what stellar physics allows. Born as massive main-sequence stars, they have already lost a significant fraction of their original mass by the time they reach this phase. Their immense size is not a sign of abundance, but of fragility. Gravity, once dominant, has loosened its grip. Radiation and turbulent convection inflate the outer layers until the star resembles a vast, luminous fog anchored to a dense core. Among the largest known candidates are stars whose estimated radii extend well beyond 1,000 times that of the Sun. In these cases, radius becomes a statistical concept rather than a physical surface. The outer atmosphere is dynamic, flowing outward even as it glows. What appears large today may be measurably smaller tomorrow. If such a star were placed where the Sun now sits, its atmosphere would engulf the inner planets and extend deep into the outer solar system. Yet despite this scale, its mass would be only a few dozen times that of the Sun, sometimes less. Size, in the late stages of stellar life, is not about how much matter exists, but how loosely that matter is arranged. These stars are astonishingly inefficient. Their density drops to extremes. A cubic meter of their outer atmosphere can contain fewer particles than the best vacuums produced on Earth. And still, they shine with hundreds of thousands of times the Sun's luminosity, their energy spread thinly across an enormous surface. This extravagance is temporary. As mass loss continues, the star contracts again, briefly becoming hotter and more compact. Eventually, nuclear fusion in the core assembles elements too heavy to release energy. Iron marks the end. When fusion stalls, gravity collapses the core in a fraction of a second. The rebound tears the star apart in a supernova, returning its material to the galaxy. What follows is not destruction, but redistribution. The gas expelled in these explosions seeds future generations of stars. Planets form from this enriched material. Chemistry becomes more complex. Life, at least in one corner of the universe, becomes possible. In this sense, the largest stars are not monuments, they are transitions. They represent a fleeting imbalance between gravity and radiation, a moment when matter is stretched almost to breaking before being scattered back into space. The universe does not favor permanence, it favors cycles. The largest stars are among the shortest lived, and their grandeur exists only briefly, suspended between creation and collapse. To ask how large a star can be is ultimately to ask how close matter can come to flying apart while still shining as a single object. The answer changes as measurements improve, as new candidates are discovered, and as models evolve. But the deeper truth remains constant. The universe permits enormity only in passing. Its greatest structures are not those that endure the longest, but those that burn brightest just before they vanish, leaving behind the raw material for everything that comes next.